Hello and welcome to our precipitation reactions and net ionic equations discussion for the solutions unit. In this video we're going to talk about one type of double replacement reaction called the precipitation reaction, and then how to further simplify that expression in a net ionic equation. Please have your notes out, closely follow the information that's given, and make sure you're practicing along with this video and come to class with questions. Okay, the precipitation reaction is a double replacement reaction. Double replacement reactions take place in an aqueous system. Okay, in other words, dissolved compounds reacting with one another, usually ionic, although covalent compounds, acids, can also participate in these types of reactions. They can yield insoluble products called precipitates, and this is an example: sodium iodide with silver chloride making silver iodide, which is a solid, and aqueous sodium chloride. And this is a reaction because of this production of this solid here. But you can also produce molecules of covalent compounds, liquids, gases, and potentially other solids. But the main idea is here something has to change. It can't simply stay in aqueous form. And when we say something's in aqueous form, being an ionic compound, it means it's in basically a group of ions. You really don't have these compounds if they're aqueous. What you really have is a group of sodium ions and chloride ions that are in hydration shells. They're coated by water molecules, attracted by that electronegativity difference and the hydrogen bonding. So the precipitates can be of all types, but typically what we'll see is a solid product. What governs this is the solubility rules that you see on the inside of the front page of your practice packet. And you do need to memorize those rules. In a double replacement reaction, if no precipitate or molecules form, there's no reaction. You will see in a few minutes in an acid-base reaction, we form water, which is a molecule, so it is a reaction. But how do you know if a precipitate forms? You look at the products of double replacement by swapping cation for anion of your given reactants, and you see if either of your products that forms is a insoluble or solid product. Usually solid. It can be liquid or gas. To determine if a precipitate forms, we'll consult our solubility rules, and here they are again. These match what is inside the front of your practice packet. But what I emphasize is you closely understand the first rule here. Most of what we do will come from this first rule. We will also need to know the exceptions to halides, sulfates that are soluble, and then their exceptions. The fact that hydroxides are insoluble except for potassium and sodium hydroxide. When we say something is slightly soluble, it's essentially insoluble. Sulfides, carbonates, chromates, phosphates are insoluble unless they're bound to something from Rule 1. So what we're going to do is we're going to make a precipitation reaction from a group of words. So aqueous lead-2 nitrate is mixed with aqueous potassium iodide. So lead is Pb, it's got a +2 charge. Nitrate, -1. So what I'm doing right now is I'm writing each thing that's given to me, but in ion form, okay? So I can see how it's going to react. And then potassium iodide. Well, for some reason that halo is staying there, but that's okay. So we have potassium, which is +1 charge, and iodide -1. We should see that we have these charges and we can manipulate this. So what products will form? Well, let's write this out. We'll have lead with +2 binding iodine, so it's going to be PbI2. Okay, that's one product. And our second product is going to be potassium, which is +1 charge, with nitrate, which is -1 charge. So we have potassium iodide and lead-2 iodide and potassium nitrate. Those are two products. So to write our reaction, we have to consider, does a product form? So to consider does a product form, we're going to say, well, lead iodide. Iodide's a halide, but if we go back to our rules, we'll see that, there you go, lead-2 is an exception, so it is insoluble, so that's going to be a solid product. And potassium nitrate contains potassium, a group 1 metal. That's always going to be aqueous. Same is true for nitrate, so this is a double whammy of soluble. So we have Pb and O32 plus, and that's aqueous, plus potassium iodide aqueous, forming, here's our precipitate, lead-2 iodide, and that's a solid. Notice I'm writing phases of matter for everything here, and potassium nitrate. And then we check and see for balancing, are we balanced? And the answer is no. We need 2 of these and 2 of those, and that should take care of our business. That is our precipitation reaction, and it doesn't happen without this solid product. Okay, net ionic equations. So far in chemistry, we've been writing molecular equations, in other words, as if everything was perfectly intact. But the reality of a solution is, if something is aqueous, it's not intact, it's in ion form. So what we're going to be doing is taking these precipitation reactions, and this is the same one we just did, just rewritten, and we're going to break it down into its parts, its actual parts. So what that means for us is, if it's aqueous, we turn it back into its ions, and we do consider how many of each ion we've got. So here we go. What we're writing now is called a complete molecular equation. So I'm going to have lead 2 ion, pardon me. I'm going to have nitrate ions. Pardon me moving this around. I'm a little wonky with my device. 2 nitrate ions. Oops, not plus, minus. Let's erase that. So, as you can see, what I'm doing is I'm going through and writing every single ion that's present in our system. I've also got potassium ion, but I got 2 of them. And I've got 2 iodide ions. Oh, come on, machine. 2 iodide ions, forming our solid precipitate. Let's write that in red. And we have 1 of this, so there's no use writing a coefficient. And then on the product side, my 2 potassium nitrates are aqueous. So I've got 2 potassium, and I've got 2 nitrate. Okay, so that is a complete ionic equation. Notice my solid product that is intact in its solid form on the product side is written that way. Everything else that's aqueous is in ion form. So a complete ionic equation, rewritten here for us again, helps us to see exactly what our solution contains. Now, writing a net ionic equation simply means we identify substances that appear both in ion form as reactants and products, and we omit them. Okay, so let's look at one. We call those ions that are present on the reactant and product side spectator ions. For example, the nitrate ions are present in equal amounts on either side of the reaction, so they cancel out. Same as 2 of potassium, they cancel out. And what is left behind is that reaction between our lead ions and our iodide ions in the appropriate quantities. Law of conservation still matters to make lead 2 iodide solid. This is the net ionic equation. Okay. The key idea here, the spectator ions will be in equal quantities. If you've balanced everything appropriately and written everything appropriately, you will see them cancel. Okay. So let's practice one together. Write a molecular, complete ionic, and net ionic for the sodium hydroxide and iron 3 chloride. So what I'm going to do is I'm going to quickly write out what I've got. Now, you're given your reactants are always going to be aqueous. Otherwise, you couldn't mix a solution of them around. Oh, I'm not seeing to be able to drop it here. Let's have iron. Look at this behavior. This is odd. So we've got iron 3 chloride, FeCl3, and that's aqueous. And then I'm going to be forming sodium chloride, and from our solubility rules we know that's aqueous, and we'll be forming iron 3 hydroxide. Now if we look back at our solubility rules, we'll see that the hydroxides, the only soluble hydroxides are sodium and potassium. So iron 3 hydroxide, and I owe you a 3 here, is going to make a solid product. Now balancing is still important, so let's go back, put our coefficients in. We need 3 hydroxides on the reactant side, and we're going to need 3 sodium chlorides on the product side. That should cover us. Now we need to write our complete ionic equation. Everything aqueous gets torn down in proper quantities, so I've got 3 sodium ions. I've got 3 hydroxide ions. I've got 1 Fe3 plus. I've got 3 chloride ions. And my products will be 3 sodium ions, 3 chloride ions, and then our same solid iron 3 hydroxide So that's my complete ionic. So now what I'm going to do is I'm going to take my black pen and I'm going to go through and cross out everything that appears as a reactant and a product. Sodium ions, cancel, 3 of them. Chloride ions, 3 of them, canceled. So that leaves me with the simple net ionic equation: 3 hydroxide ions, 1 iron 3 ion. Oops, let's make that an arrow. And then our iron 3 hydroxide solid. So that solid product, iron 3 hydroxide, if you're painting a picture of what's happening in your mind here, is if you're watching this thing happen, you would see these 2 aqueous things come together. The sodium hydroxide and the iron 3 chloride come together, and when you put them together, some sort of precipitate forms in your system, something that otherwise was not there before. 2 clear solutions become this solid iron 3 hydroxide. The sodium and chloride ions that still remain are just incidental. Okay, they're part of the system, but they are not at all reacting. Those are spectators. We have one more. This time we've got sodium nitrate and calcium chloride. So a little more quickly this time, sodium nitrate plus calcium chloride, and we can always assume that our givens must be aqueous, otherwise we don't have any possibility for reaction. Well, we may have a possibility for reaction, but not this type. So sodium would bind chloride in HCl, that's aqueous, and calcium would bind nitrate. Calcium nitrate being -1 would form CaNO3 2. But you look at your solubility rules and you see that nitrate is always soluble. Okay, so this means you've made a system of ions that don't do anything. This is no reaction. No reaction. Okay, so that pretty much wraps up net ionic equations. If you have any questions about what we've done so far, about the practice for net ionic equations, please come see us in class. Please ask questions and we will do our best to help you out. Otherwise, practice hard. Test on the 14th. See you on the next one.